Good morning all, welcome back to plus 2 physics class. In the last class we started the topic magnetic field lines. Okay, in that session we discussed what is magnetic field lines. Okay, what is the magnetic field lines? Today we are continuing that topic, that is the next session is characteristics of magnetic field lines. Okay, characteristics of magnetic field lines. Okay, what are the characteristics of magnetic field lines? Here the first characteristics of magnetic field lines is, what is the first one? The magnetic field lines are always closed. Okay, the magnetic field lines are always closed. Okay, this is closed, like a closed loop. Okay, that is its magnetic field lines are always closed. Yeah. Okay, and the second property, the tangent. Okay, the tangent at any point on a field line gives the direction of magnetic field at that point. Okay, that is the tangent at any point on the field lines gives the direction of magnetic field at that point. That is, we draw a tangent in the magnetic field lines. Okay, that tangent direction gives what? Direction of magnetic field at that point. Okay, that is, we consider a point on a magnetic field and draw a tangent from that point, and the tangent gives the direction of magnetic field at that point. Okay, and the third property is, in a uniform magnetic field the field lines are parallel to each other. Okay, parallel to each other. Okay, in a uniform magnetic field, the magnetic field lines are parallel to each other. Then the fourth property or characteristics of magnetic field lines is, no two field lines will intersect each other. Okay, there is no two field lines will intersect each other. Okay, if they intersect, the magnetic field will be having two directions at that point. Okay, which is not impossible. Okay, which is impossible. Okay, yeah, that is, there is no intersection between two magnetic field lines. Okay, if they intersect, the magnetic field will have two directions. Okay, at that point, which is impossible. Okay, then the last property. Okay, the last property is, the number of field lines passing normally through a unit area taken around a point gives the intensity of the magnetic field at that point. Okay, that is, the magnetic field lines passing through a unit area. Okay, unit area, that is, passing normally through unit area around a point gives the intensity of the magnetic field. Okay, intensity of the magnetic field. Okay, these are the properties of magnetic field lines. Is it clear? Okay, next we are going to discuss the topic bar magnet and solenoid. Okay, bar magnet and solenoid. That is already discussed. What is bar magnet and its properties, and what is solenoid and its properties. Okay, listen here. When a current is passing through a solenoid, it behaves like a bar magnet. Okay, when a current is passing through a solenoid, okay, through a solenoid, it behaves like a bar magnet. Okay, at the two end of the solenoid, at the two ends, North Pole and South Pole are developed. Okay, at the two ends of the solenoid, North Pole and South Pole are developed. Okay, when we look at one end of the solenoid, if the current is flowing anti-clockwise direction, okay, if the current is flowing anti-clockwise direction, then that end is North Pole. Okay, North Pole. If the current flowing in clockwise direction, okay, if the current passing through in clockwise direction through the solenoid in clockwise direction, that end is South Pole. Okay, that end is South Pole. Clear? Okay. If a current I flow through a solenoid having an area of cross section A and the number of turns N, then what is the magnetic moment of solenoid? That already discussed. What is that? M is equal to NAI. Okay, M is equal to NAI. Clear? Okay, and in this figure you see the lines of force around a bar magnet. Okay, and that figure, that is you see in the circular shape, in that inside that circle north and south is marked. That is, if the current is flowing anti-clockwise direction, the end is considered as North Pole. Okay, if the current is flowing clockwise direction, okay, clockwise direction, the end of the solenoid, the considering end of the solenoid is taken as South Pole. Okay, next we are going to discuss the topic Gauss's theorem in magnetism. Okay, the Gauss's theorem in electrostatic we already discussed. Here we are going to discuss Gauss's theorem in magnetism. Okay, this is a small topic. That is, this Gauss's theorem states that the surface integral of magnetic field over a closed surface is 0. Okay, Gauss's theorem states that the surface integral of magnetic field, okay, surface integral of magnetic field over a closed surface is 0. That is, integral B dot ds, surface integral of B dot ds equal to what? 0. Here B is the magnetic field. That is, the surface integral of magnetic field over a closed surface is 0. Okay, that is integral B dot ds equal to 0. Okay, this is Gauss's theorem in magnetism. Okay, next we are going to discuss the topic magnetic properties of materials. Okay, that is, what are the magnetic properties of materials? Okay, the first magnetic property of material is magnetizing field. Okay, magnetizing field. This magnetizing field is represented as the capital letter H. Okay, listen, what is magnetizing field? When a magnetic material is placed in a magnetic field, it becomes magnetized. Okay, if a magnetic material is placed in a magnetic field, it becomes magnetized. Okay, magnetized. The ability of the applied field to magnetize the substance is measured by the quantity magnetizing field. Okay, what is that? The ability of the applied field. Okay, the ability of the applied field to magnetize the substance. Okay, to magnetize the substance is measured by the quantity. Okay, that quantity is called magnetizing field, and it is denoted by the capital letter H. Clear? Okay, and the magnetizing field along the axis of a solenoid having n turns per unit length and carrying a current I is given by H is equal to Ni. Okay, let us consider a solenoid having n turns per unit length. Okay, n turns per unit length and carrying a current I. Then the magnetizing field H equal to what? Ni. Okay, H is equal to Ni. Okay, this is the first property, that is the magnetizing field. Clear? Okay, then the second property, okay, magnetic property of material. Second property is permeability. Okay, permeability, and it is denoted by the letter mu. Okay, mu. Listen, the permeability is the ratio of magnetic field strength or magnetic flux density B in a material to the magnetizing field. Okay, that is the ratio of the magnetic field strength to the magnetizing field is called the absolute permeability of the medium. That is mu equal to B by H. Okay, mu equal to B by H. Here B is the magnetic field strength. Okay, magnetic field. Okay, and H is the magnetizing field. That is the ratio between the magnetic field strength to the magnetizing field. Okay, or this equation B equal to, from this equation what is B? B equal to mu H. Okay, mu H. Here mu is equal to what? Mu 0 mu r. Okay, mu 0 mu r. Okay, mu 0 mu r. That's already discussed. Okay, for a free space, what is mu? Mu equal to mu 0. Okay, for a free space, mu equal to what? Mu 0. Then what is B? B equal to mu 0 h. Okay, mu 0 h. Clear? Okay, this is the what? Permeability. This is the second property of the magnetic materials. Clear? Next property, that is the third property, is intensity of the magnetization. Okay, intensity of the magnetization, and it is represented by the letter or denoted by the letter capital letter M. Okay, capital letter M. The intensity of the magnetization is defined as the magnetic moment developed. Okay, the magnetic moment developed per unit volume. Okay, that is the magnetic dipole moment or the magnetic moment per unit volume of this specimen when subjected to a magnetic field. Okay, that is the magnetic moment per unit volume is called what? Intensity of the magnetization. Okay, intensity of the magnetization. That is the intensity of the magnetization, capital letter M equal to M by V. Okay, this small letter M is magnetic moment or magnetic dipole moment. Okay, divided by what is V? V is volume. Okay, volume. Then what is M? We have M equal to P into 2L. Okay, substituting that P into 2L divided by what is volume? Length into breadth into height. Okay, length into breadth into height, or area into length. Okay, area into length. That is, here area is taken as A. Okay, A into what is the length? 12. Okay, that is A into 12. What is the A into 12? Volume. Okay, here 12 and 12 is cancelled. then what is the balancing one? P by A. That is pole strength per unit area. Okay, that is this intensity of magnetization, also defined as the pole strength per unit area. Okay, the pole strength per unit area. Okay, this is the third property. Okay, then the last property, that is susceptibility. Okay, susceptibility. Listen, the magnetic susceptibility is defined as the ratio of intensity of magnetization. Okay, the intensity of magnetization produced in a material to the magnetizing field. Okay, to the magnetizing field. What is that? The ratio of intensity of magnetization. Okay, the ratio of intensity of magnetization produced in a material to the magnetizing field. Okay, that is the susceptibility chi m, the letter representing chi m, that is magnetic susceptibility chi m equal to mu by h. Not mu by h, m by h. Okay, m by h. Here m is the intensity of magnetization. Okay, and what is h? H is the magnetizing field. Clear? Okay, this is the properties. Okay, magnetic properties of materials. Okay, next we are going to start our new chapter. That is our 8th chapter, electromagnetic waves. Okay, electromagnetic waves. This is a small chapter. In this chapter, we are going to study what is electromagnetic waves and what is the nature of electromagnetic waves and properties of electromagnetic waves, and what are the 7 types of electromagnetic waves and its spectrum. Okay, that is discussing in this chapter. Okay, this is very small chapter. Okay, what is electromagnetic waves? The electromagnetic waves are time varying electric and magnetic field that propagate in space. Okay, an electromagnetic waves are time varying electric and magnetic fields that propagate in space. Okay, this electromagnetic wave are experimentally confirmed by Hertz. Okay, that is Hertz is experimentally confirmed the existence of electromagnetic waves with the help of a spark gap oscillator. Okay, with the help of a spark gap oscillator, Hertz experimentally confirmed the existence of what? Electromagnetic waves. And electromagnetic waves are one of the main prediction of Maxwell's equation. Okay, that is one of the main prediction of Maxwell's equation is electromagnetic waves. Okay, and Xii Bose produced electromagnetic waves of smaller wavelength. Okay, smaller wavelength, that is in the range of 5 millimeter to 25 millimeter. Okay, that is Xii Bose produced electromagnetic waves of smaller wavelength in the range of 5 millimeter to 25 millimeter. Okay, and one more thing, the Marconi is discovered that electromagnetic waves can radiate up to several kilometers. Okay, that is Marconi discovered that the electromagnetic waves can radiate up to several kilometers. Okay, this is just an introduction for electromagnetic waves. That is what is electromagnetic waves and who experimentally conferred the existence of electromagnetic waves, and who first produced electromagnetic waves for smaller wavelength. Okay, is it clear? Okay, next we are going to discuss the topic nature of electromagnetic waves. Okay, the first one, an electric charge is oscillating with a frequency. It produces electromagnetic waves of the same frequency. That is, we oscillating an electric charge with a frequency, it will produce what? Electromagnetic waves of the same frequency. Okay, this is the first nature of a electromagnetic wave. And the electric and magnetic fields in a electromagnetic wave are perpendicular to each other and to the direction of propagation. Okay, what is that? The electric and magnetic fields in a electromagnetic waves are perpendicular to each other and to the direction of propagation. Okay, direction of propagation, that is, it act like a transverse wave. Okay, that is the property of transverse wave. Clear? And this is the pictorial representation of electromagnetic wave, and this is very, very important. Clear? Okay, in this figure you see the three axes: x-axis, y-axis and z-axis. Here the direction of propagation is in the direction of z direction, and the electric and magnetic field are perpendicular to this axis. That is, the electric and magnetic fields in a electromagnetic waves are perpendicular to each other and to the direction of propagation. Clear? And in the case of electromagnetic waves, the electric and magnetic fields are represented by Ex equal to E0 sine kz minus omega t, and the magnetic field By equal to B0 sine kz minus omega t. Okay, here k is related to the wavelength lambda. Okay, k is related to the wavelength lambda of the wave by the equation k equal to 2 pi by lambda. Okay, k equal to 2 pi by lambda. Okay, clear? That is, here the electric and magnetic field are represented by Ex equal to E0 sine kz minus omega t, and By equal to B0 sine kz minus omega t, and here k is related to the wavelength and the equation k equal to what? 2 pi by lambda. Okay, 2 pi by lambda, and the speed of propagation. Okay, the speed of propagation of the wave is omega by k. Okay, the speed of propagation of the wave is omega by k, and the magnitude of the electric and the magnetic field in a electromagnetic waves are related as B0 equal to E0 by C. Okay, E0 by C. And here B0 and E0 are the magnitude of the electric and magnetic field of electromagnetic wave, in an electromagnetic waves. Okay, these are the nature of electromagnetic waves. Okay, next we are going to discuss the properties of electromagnetic waves. Okay, what are the properties of electromagnetic waves? Okay, the first property, they are self-sustaining oscillations of electric and magnetic fields in free space or vacuum. That is, the electromagnetic waves in free space, they are self-sustaining oscillations of electric and magnetic field. Okay, this is the first property. And the second property, this electromagnetic waves are shows transverse wave nature. Okay, transverse wave nature. Okay, that is already tell in the case of nature of electromagnetic waves, that is the electric and magnetic field are in the direction of perpendicular to the direction of propagation of the electromagnetic waves. Okay, therefore this is in transverse wave nature. Okay, that is the electromagnetic waves shows transverse wave nature. Okay, third property, no material medium is needed for its propagation. Okay, there is no material needed for transmitting, or no material medium is needed for the its propagation. That is, it will travel in every medium. Okay, in every material medium. Okay, that is the electromagnetic wave, no material medium is needed for its propagation. Okay, and the fourth one is electromagnetic waves are not deflected in electric field and a magnetic field. Okay, that is, electromagnetic waves are not deflected in electric field and a magnetic field. Okay, and the next property, the velocity of electromagnetic wave in any medium is given by u equal to 1 by root mu epsilon. Okay, mu epsilon, v equal to 1 by root mu epsilon. That is, the velocity of electromagnetic waves in any medium is given by u equal to 1 by root mu epsilon. Okay, and the next property, the electromagnetic waves are polarized. Okay, the electromagnetic waves are polarized. And the next one is, the electromagnetic waves carry energy and momentum like other waves. Okay, that is, electromagnetic waves carries energy, momentum like other waves. Okay, clear? And the last one is, if the total energy transferred to a surface in time t, okay, in time t is u. Okay, if u is the energy transferred to a surface in time t, the magnitude of the total momentum delivered to the surface is given by P equal to u by c. Okay, P equal to u by c. Okay, this is the last property. Okay, these are the properties of electromagnetic waves. This is very important topic. Okay. Okay, I hope you all understands today's class. That is, today we finished the chapter magnetism, and just started new chapter, that is electromagnetic waves. In this chapter we just discussed what is electromagnetic waves and the nature of electromagnetic waves, and what is the properties of electromagnetic waves. Okay, thank you.